Hello, everybody. Hope you are doing well. This is the video of me going over some notes for the e-learning on this Monday and Tuesday, and hopefully I'll be seeing you guys back after that. I don't know what the plans are or anything like that for this one day. I'm just going to make this video. In the future, if we do more e-learnings like this and so on, I don't know what it's going to be, but if we do, I may do more like just Google Meet in class and go through stuff with you that way, or I may just do stuff like this because it's, um, well, we'll see how it goes. Okay. Might hear my dog drinking. I'll try to go through quickly. But basically for today, I'm going through I'm going through some notes for the specifics of muscle contraction. Last time, when we were in class, we went through action potentials and how action potentials work. That is essential for understanding this. So if you weren't here for the action potential stuff or anything like that, those notes are complete online. Just the notes probably may not do it, especially if you've never learned about that kind of stuff before. It may be useful to look up some videos or ask me questions and stuff like that. But if you don't understand action potentials, you're not going to do well here. Okay. So that's what this is going to be over. Like I said, I'm going to try to go through it at a good pace, and hopefully it's not too long of a video. Okay. Here's my dog. Here, come here. Say hello. Where'd you go? Come here. There he is. Hey, bud. This is Daisy. Here's Luna. Hey. You'll probably hear them in the background. Hello. Yes. Okay. Move. All right. So let's go ahead and get into it. You should be able to still see me now. I can't see the camera when I do this, but it should work just fine. Okay, so like I said, this is all about muscle contractions. We talked about some basics of muscle contractions with muscle introduction and everything like that towards the beginning of this unit. This is the more specifics of how action potentials work in muscles. Okay, so we're getting more specific with that. All right, so and if my face cuts anything off in the corner there, I apologize, but I tried to move everything so that it should be, you should be able to see everything. Okay. All right. So muscles to start things off. Okay. A few ground rules and some vocab we're going to be using. Muscles must be stimulated by a motor neuron, which is a nerve cell, in order to contract. Okay. That's the only way that it works. And if you were here when we talked about action potentials, I showed you the muscle stimulator and everything like that, and you might be wondering, well, that electricity causes a muscle contraction as well. So isn't that something different that's not causing a muscle contraction that's not a neuron? It's the electricity from that device is tricking the neuron to fire. Fire meaning it causes that action potential with the sodium rushing in, the potassium out, and flipping and all that stuff. So it's still that motor unit, which we're going to talk about in a second. That muscle fiber is still getting contracted due to a stimulation from a motor neuron. Okay, so I use the word motor unit. You might have heard this word before. A motor unit is one motor neuron, which a motor neuron is a type of neuron that makes something move, like the ones that are attaching to muscles, of course. One motor neuron and all the skeletal muscle cells stimulated by that neuron. Okay, so that together, that unit is called a motor unit. Okay, I left a blank slide here because I want to try to draw this. Where is, there we go. Okay. So if we've got a bunch of muscle cells, muscle fibers, right? Muscle cell, muscle fiber, muscle fiber, muscle fiber. These are, I don't know why I'm bending them upwards like that. Imagine those are muscle fibers, okay? And we've got a motor neuron. Okay, it's got a nucleus, and this is the body of that cell, and then we've got the axon that comes off of that. We'll define that again in a moment. And then that axon is going to branch off. Let's say one connects here, not actually connecting, we'll talk about that in a sec, branches off and connects over here. So like that would be a motor unit, and perhaps there's another nerve cell. I'll draw this one a little rougher and quicker, that goes over and attaches like one to here, and then one to over here, and one to over here perhaps, and those trigger well, let's go ahead and just do all of them. There we go. So that would be another motor unit. Okay. And different motor units could be attached to differing numbers of muscle fibers. And there's also something we haven't talked about, but some muscle fibers, muscle cells, will be thicker, stronger than others. So like, let's say this is a bigger, thicker, stronger one. And so is this one. There's a better way to do this, I'm sure, but and so is this one. These ones are all thicker and stronger. Okay. Imagine if this looked better. And these ones are pretty thin, right? So as you can imagine, your muscles doing a certain movement is going to either activate this one, we'll call this 2, or this one, we'll call it 1. So the activation of motor neuron 1 is going to result in a different contraction style or contraction type or strength of contraction rather than motor neuron number 2. Okay. So moving on, there are, like I said, different types of motor units. They're not all the same. They can have differing numbers of neurons, and they can have differing size and strength and contractile speed and so on and so forth based off of the type of neuron and the type of muscle fibers that they're attaching to. So differences in size of motor neuron, as well as how many fibers and the strength and size of those fibers they attach to, give us the wide range of muscle movements that we can undergo, right? So obviously, there's a big difference between your body doing something like something fine with your hands, like tying a knot with thread or something like that, something really delicate, or you're drawing something really precise, or picking up a tiny object without breaking it, as opposed to chopping wood or picking up a tree or sprinting away from an animal that's attacking you or whatever. There's a wide variety of muscle movements that a human's going to need to undergo, right? We're going to get a little bit more into these in the future when we go through ATP and how muscles actually get energy out of, or how muscles and energy work together. But we'll talk about it a little bit here. There's 4 types here. I'm ignoring one because one's like a certain intermediate that you sometimes don't hear about. But so if you Google this, you should find 4 types of motor units. I'm just focusing on 3 here, okay? And these are generally kind of boxed into being called slow twitch or fast twitch. The slow motor unit, this first one here, being a slow twitch, and then the other one's being a fast twitch. Okay, so you can have what's called a slow motor unit or an S unit, which is, as the name suggests, slower. It's important for sustained contractions, smaller forces. It's the flip side though is that it's highly fatigue resistant. Okay, and the reason for this is because it's got lots of mitochondria. Okay. More mitochondria means more energy available. Less mitochondria means less energy available, and so you can run out more quickly. So, like the muscles in your spine, the erector spinae, those are the muscles back here that are keeping you erect while you're standing and so on. Those, like we said in the trunk muscles one, are pretty much always activated, like all day long. Or when you get home from a long day and you lay down in your bed, it makes your back feel really nice. It's because those muscles have been activated pretty much all day long. And the reason why that's possible is because they're being activated largely by slow motor units or S units. Contrast that with these other 2 types, fast fatigable motor units or FF, which are high force, fast contraction, very susceptible to fatigue. So these 2 contrast with each other a lot. Sparse mitochondria, this is stuff like running, jumping, lifting. You know, it's pretty easy to tell the difference, right? How long can a person sprint? Even if you're healthy, if you're sprinting full speed, you can't do it for that long, right? As opposed to how long can a person jog? That could be a very long time. Those are different muscles being used, right? And then you have these fast fatigue resistant motor units, which are kind of an intermediate in force, size, and speed. So depending on what action, you're going to get a combination of these different actions, right? Or maybe only one certain type, depending on the thing that's being done. We'll learn more about like mitochondria and stuff like that, and the coloring of these muscles and stuff like that more in the future, but I want you to be aware there's different types. Okay. Here's a graph, just image of some data showing the stimulation of these different types of motor units and what they look like. So here's fast fatigable and fast fatigue resistant, the FF, and then the slow, the S units. you can see the difference here, particularly looking at how quickly they fatigue, right? So like right here, those are the fast, fatigable. That's like the big lifting something really heavy, sprinting. The drop down in how effective they are is steep, as opposed to the ones that are really fatigue resistant, which are much more sustained over time. Okay. Let's see. Okay, so some basics. We talked about basics of what a nerve looks like, that right there. Words I'm going to be using: axon. The axon is from here over to, well, here. This whole thing is the axon, okay? More specifically, something called the axon terminal are the ends of the axons that meet the tissue and deliver the message that's being sent. For tissue, we're talking about muscles for this section, right? But, whoops, well, so like, that's an axon terminal, it's an axon terminal, axon terminal, axon terminal, axon terminal, blah, 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 right? So like what I was drawing over here, so like that would be an axon terminal, that would be an axon terminal. Okay. I'm going to use those words as we move forward. Other ones you're going to see: neuromuscular junction. This is the place where the axon terminal actually meets the sarcolemma of a muscle cell. Though, and you've maybe heard this before, the neuron and the muscle cell actually never touch. There's a gap, and we call that gap the neuromuscular junction. There's a space in between the two. So if I've got a nerve and I've got the muscle fiber, there's a space in between the two where they never actually touch. And we'll talk about what happens in between there. That space is called the synaptic cleft. That's the gap outside the axon terminals that's filled with this thing called an interstitial fluid. That part's not super important, but yeah, we'll use that word as well in here. Okay. So we've seen this image once before. So zooming here, looking at the right picture over here, this area is the spot that I was talking. So like all this stuff, this is space in between what is the nerve here. So like that's nerve, and then this is the muscle over here. That's the space in between. And there's a transfer in the action potential from the nerve, which is caused by the rushing in of sodium and the change in the flipping of the charges, and that opening the next sodium channel, which causes sodium to rush into that one, which causes the next, blah, blah, blah. That signal that we talked about with action potentials when I saw you guys last. That gets sent to the end here, which again, we're talking about an axon terminal, zoomed in on one of those heads there. That gets transferred to a chemical signal that diffuses across this space here, which again we call that the synaptic cleft. And that signal gets sent to the muscle by this chemical neurotransmitter being diffused across this space right here. And that in turn will cause the action potential in the muscle fiber. We're going to go through that in some steps. Okay, so here is muscle contraction very simplified in these 4 steps. I say very all caps because it is very simplified. And even what we're going to talk about in the slides afterwards, it's still very simplified, right? We're not getting into the nitty-gritty details. But here it is summarized really easily before we move forward, okay? So, for a muscle to contract, first step, there's a neuron action potential. That's what we talked about with the sodium rushing in, causing the next one, the next sodium pump to open, and sodium rushing into that one, and causing that domino effect. There's a neuron action potential. Then, at that bulb, the end, the axon terminal, there's a neurotransmitter release. There's lots of different types of neurotransmitters. We'll talk more about them with the nerve nervous system unit. Here, I do want you to know this. The neurotransmitter is called acetylcholine, or ACH. And that is what's getting diffused across that space. That triggers a muscle fiber action potential. So that signal, that domino effect is getting sent from the nerve to the muscle, and then it's continuing through the muscle, causing that muscle contraction, which is through something we call the sliding filament theory, which is all the stuff that we talked about. We've talked about already with the myosin and the actin, and causing those the actual muscle contraction of the muscle in those sarcomeres. Okay, so more specifically, steps of muscle contraction. So there's an electrical signal, a nerve impulse, that is sent down the axon to the axon terminal, which is at the neuromuscular junction outside the synaptic cleft, right? So we're talking about this area right here, okay? The nerve impulse releases a neurotransmitter from the axon, which is acetylcholine, or ACH. Okay, so again, the ACH would be these little guys. That's a bunch of ACH inside of a vesicle, inside that nerve cell. Okay, and again, this image is a zoomed in part of that right there. All right. Acetylcholine diffuses across the synaptic cleft to the membrane receptors of the sarcolemma. Sarcolemma, remember, is the membrane of the muscle fiber, which is a muscle cell. So this is the sarcolemma, this kind of whitish area that I've drawn over. Okay, and it's got their own sodium proteins that are able to move. Trying to figure out a good way to say this, to transmit the signal of ACH into an action potential in the muscle fiber. Okay, and that is where this is happening. Okay. Then, if enough acetylcholine is released, so if enough of these guys are released, the sarcolemma becomes more permeable to sodium ions by opening protein channels. So these will only open up to take in sodium if there's enough ACH. Okay, so there's another aspect here of a potential being reached, a threshold being reached. All right, so if there's not enough ACH, the sodium pumps will not open up, and the sodium will not rush in. There will not be a new action potential created in that muscle fiber, and nothing happens. Most of the time, though, it does happen. Okay, so if it does successfully happen, those protein channels open up, domino effect happens, and this begins an action potential in the muscle fiber. Okay, so we're almost done. The thing that will happen because of that is what we call the sliding filament theory. Okay, we've talked about this before, but this is good review. Those thick myosin fibers, and again, we're talking about the proteins within the organelle within a muscle fiber, which are called myofibrils, have those large projections called myosin heads. We talked about this a little bit. The myosin heads love to grab the thin actin fibers, or filaments, and pull them toward the M line. Remember, with this here, there's the M line in the middle that anchors those, the myosin, and the actin is going to be close to that myosin. And the myosin is going to want to grab that actin and pull it, never push, pull it towards that M line. So when they have it sitting like this, I think you can see me, and that myosin is going to take that actin and make it do this motion. That's only going to happen because of the steps that we went through over here. Okay. So the myosin heads alternate grabbing and pulling, so the actin filaments are basically walked towards the M line. Okay. So again, this is the M line right here. The thick red is the myosin. The thin blue is the actin. And this is where those heads are going to be. Let me get a different color. Can I not select a different color? Here we go. What would be good here? White. So the myosin has those special parts to it called the myosin heads, which actually do the grabbing and the pulling. So there's going to be, let's see, where's the best place to draw this? So if there's one here, it's got the little head part there, and then here it's got the little head part there. I'm doing this just with a mouse. There's probably a better way for me to do this. And then there's some down here, some down here. And so they will attach to that actin, and they will pull in that direction. These ones, if you imagine those heads coming into contact and then pulling it that way. These ones down below coming into contact and pulling it that way. And these are happening all along these different areas here. So if you imagine all of those at every part here in this sarcomere, this is also happening over here as well. These guys are pulling in this direction, pulling that direction. These guys are pulling this direction. That causes the shortening of that muscle fiber, right? Those are the these are the heads right here. I should probably put this back to red. Those are the heads I was talking about. So this is the myosin head before it's told to be pulling, and then there it is actually pulling. Imagine it going that direction, right? So last few important things here. Those myosin heads, these guys here, things that are doing the pulling, cannot attach to the actin filament unless that action potential occurs. Okay. Here's why. Myosin binding sites are blocked by these things called regulatory proteins. Specifically, they're called troponin and tropomyosin. These, I do actually want you to know the names of these. Okay. They are, I don't need you to like have to label them on an actin or anything like that, but they are points that are blocking. There's a lot of chemistry going on here. If you're curious about what all this means, like what does it mean for a binding site to be blocking something, to be blocked by a regulatory protein or whatever? It's a lot of chemistry, but basically, troponin and tropomyosin's job is to block the myosin binding sites so that myosin's just not pulling all the time. Myosin heads want to be pulling all the time. That's what those proteins are designed to do. They want to bond there and pull. The binding sites being blocked is what stops that from happening. Otherwise, obviously, your muscles will be continuously contracting all the time. So, how this is regulated. Way back when we talked about parts of muscle fibers, we talked about the sarcoplasmic reticulum, and I told you its main job is to wrap around the myofibrils, and it controls calcium, has to do with calcium, and then we would talk about it later. Here we are talking about it. Calcium, specifically Ca2+, is released into the cytoplasm by that sarcoplasmic reticulum, the SR, only when stimulated by an action potential. So the events that have happened here is the nerve sends the signal, it gets to the muscle. I'm simplifying, obviously. It goes through the muscle. That action potential causes calcium being released into the cytoplasm by the sarcoplasmic reticulum. Why does that matter? The calcium binds to the regulatory proteins, moving them out of the way and exposing the binding sites, allowing myosin heads to work. So there's a cascade of events here, right? This is all about cascading events, dominoes. If you don't have the action potential, you don't have the release of calcium. If you don't have the release of calcium, it will not bind to the regulatory proteins. If it doesn't bind to the regulatory proteins, then they will stay put. If they stay put, then the myosin heads can't attach and there's no contraction. So for the contraction to happen, you have to have that beginning step cause that cascade of events. You have to have the calcium that binds the regulatory proteins, moving them out of the way so that the myosin heads can bond to the actin and cause that actual contraction to happen. Okay, so action potential in the neuron, the nerve impulse, plus action potential in the muscles, plus that sliding filament theory, that is what a muscle contraction actually is. And as a side note, I might have you guys research some types of this, but that calcium uptake and everything like that, the sarcoplasmic reticulum, troponin and tropomyosin, those are all proteins, or regulated by proteins. And you, as any protein, because proteins are made from the instructions from DNA to RNA to protein, you can have mutations that change the effectiveness or increase the effectiveness of troponin or tropomyosin and so on. There's a lot of reasons why different people cannot have certain anesthetics. You maybe heard like, you know, this of someone who can't go under or take a certain anesthetic for a surgery, stuff like that. A lot of those actually have to do with the things in those anesthetics affecting calcium uptake. Some of them actually increase it to the point where it causes the I'm simplifying this, but it causes a lot of action in the muscles, a lot of contracting, and attempting to contract, and it actually, because of that energy usage, the ATP usage, which releases heat, can actually kill you because it makes the inside of your body too hot. So that's one potential negative thing, but I'm getting too specific without you guys knowing enough for me to talk about the specifics. Okay, but yeah, you can have like someone's troponin and tropomyosin not working properly or working too well, so that muscles relax or contract too much or too little. You can have all kinds of different mutations and things here of varying difficulties and seriousness. Like if one was going to affect the way that your heart beats with its troponin, that can cause muscle or the heart failure and of course death. So it all depends. Okay, so here it all is again simplified altogether. All right, nerve impulse sent down the motor neuron. Nerve impulse makes the neuron release acetylcholine, ACH. That acetylcholine diffuses across the synaptic cleft to the muscle sarcolemma. That sarcolemma is the membrane of the muscle cell or muscle fiber. Sarcolemma lets in sodium, a bunch of it. Sodium causes the buildup of charge and causes a new action potential. That charge shoots down the muscle fiber, which I said is an action potential. The action potential makes the sarcoplasmic reticulum release Ca2+, which is calcium. The calcium moves the regulatory proteins and on actin and moves them out of the way so that myosin can move those actin filaments towards the M line, shortening the sarcomere, which gives you contraction. Okay? It's a note for me to stop there. So super vocab heavy. There's a lot of things going on here. I want you to know the basic steps of how muscle contraction works, those cascading events. If I give you images like any of these, you should be able to label them, use them to describe how muscle contraction works. We're going to talk about this more, but if I told you that a certain disease or a certain mutation increases calcium uptake or decreases troponin effectiveness or so on and so forth, you should be able to tell me what would likely be the outcome of that and really understand how this process works and fits together. Yeah, I think that's everything. Also these different types as well, being able to understand the basic difference of those, but we're going to go through the more details of those in the future. Okay, so for this unit, the rest that we're going to talk about is energy and the other different muscle types, and we'll do some stuff with muscle fatigue and muscle energy and different types of muscles and muscle attachments, practice more with those. Yeah, that's it for now. So I'm going to, let's see, discard this and stop. See you guys later.